The next series of videos are going to be about second order systems. We'll be looking at their frequency response and their step response, but we'll start off by looking at their frequency responses. First, a reminder of what a second order system is. The order of a system is the number of poles in its frequency response. So a second order system has 2 poles. It's also equal to the maximum power of j omega in the denominator of the frequency response. Second order systems have a maximum power of j omega of 2, so they have quadratic expressions in their denominator. Now quadratics have 2 roots. Those roots are the poles. So a second order system has 2 poles in the frequency response. If we have a look at the general form of the frequency response that we've seen before, it means that down here there are 2 of these bracketed expressions. There are 2 poles. There can be up to 2 zeros as well. So a second order system can either have 0 or 1 or 2 zeros. We won't see any examples with 3 zeros, because if you had 3 zeros, that would imply that at very high frequencies, the gain, or the magnitude of the frequency response, tended to infinity. And that doesn't happen in any practical circuit that we're going to be looking at. There are a very large number of different types of second order system. We'll only be able to look at a few of them in these videos, but we'll start off with a very simple one. This one. It's only got 3 components, a resistor, an inductor and a capacitor. The 3 components are in series. That makes it easy to work out the frequency response. And you can just apply the potential divider equation as we've done many times before and multiply up the numerator and denominator by j omega c in order to get polynomials on the top and the bottom, and we'll end up with this form of the frequency response. And we can instantly see that this is a second order system because it's got a maximum power of 2 in the denominator. We have a quadratic expression down here. That means we have 2 poles. In a frequency response, we might expect each pole to cause the gain to decrease at a rate of 20 dBs per decade after the break frequency of that pole. So, if the break frequency of the poles were, say, there and there, this is log of frequency, then there are no zeros at all, so we can see that at very low values of omega, this frequency response would just tend to be 1 divided by 1, or 1. 1 expressed in dBs is 0 dBs, so at low frequencies we would expect the frequency response of this circuit to start at 0 dBs, and then the Bode approximation would tell us that we would go out to the break frequency of the first pole, start heading down at 20 dBs per decade, get to the second pole, and then we would start heading down by 40 dBs per decade, because now both poles are pushing the frequency response down at 20 dBs per decade. And that is the form of the frequency response we would expect. And if we simulate it, that's exactly what we see. Starts off horizontal, low frequency, heads off down at 20 dBs per decade here, but there's another sort of bend around about here, where the second pole cuts in, and here we're dropping at 40 dBs per decade. To work out where these pole break frequencies are, we have to work out where the poles are, and that means solving the quadratic equation on the denominator of the frequency response. In this particular case, our quadratic equation was j omega squared LC plus j omega times CR plus 1 on the denominator. Set that equal to 0 to find its roots. That's a quadratic equation. We can apply the standard quadratic formula that the roots are minus b, in this case minus CR, plus or minus the square root of a b squared, c squared r squared, minus 4 times A, LC, times C, 1, all over 2A, 2LC. And that gives me the values of j omega where the quadratic expression equates to 0. In other words, these are the poles. If I do a little bit of algebra on this expression, I could conveniently divide top and bottom by c, and that would give me minus r over 2l plus or minus the square root of r squared minus 4l over c over 2l. As I've done on the slide, I could go one stage further and divide top and bottom by l as well, and that would give me minus r over l over 2 plus or minus the square root of r over l all squared minus 4 over lc all over 2. Doesn't really matter. Once you plug in the numbers, you'll get the same results. That will tell you the pole frequencies. The modulus of the pole frequencies is the break frequencies, and then you can then sketch out the Bode approximation. Except that having to solve quadratic equations is a bit tiresome and awkward. And it would be nice to be able to produce the Bode approximation or something similar to it without having to solve a quadratic equation. And it turns out that there is a useful and simple technique for doing that, and we'll discuss that in the next video. So that's all for this time. Next time, we'll have a look at that technique for working out an estimate of the frequency response without solving the quadratic equation. And that will require us to introduce the concepts of the resonant frequency and the Q factor.